Let's push this quadrature amplitude modulation a little bit further. Instead of using 2-bit symbols, let's use 4-bit words. So our incoming binary signal is now divided into 4-bit words. So this is a serial in to 2-bit out shift register. We'll take the 2 least significant bits to the top line through a digital to analog converter. So with 2 bits, the possibilities are 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. This digital to analog converter produces an output of -3 volts. So 0, 0 input maps to -3 volts out. 0, 1 input maps to -1 volt out. 1, 0 in is +1 volts out, and 1, 1 in maps to 3 volts out. That is the in-phase signal, which is mixed with the in-phase carrier and then applied to the summing amplifier. The more significant bits go through the quadrature mixer, and using the same digital to analog converter with 2 bits. There's 4 possible inputs: 0, 0, which maps to -3, 0, 1 maps to -1, 1, 0 maps to +1, and 1, 1 maps to +3. And then that is the quadrature signal, which is then mixed with the quadrature carrier and added to form a quadrature amplitude modulated signal. And the amplitude will be clearly modulated in this signal. It wasn't with the other phase shift keyed signals. So what I want to do, I want to draw the constellation diagram. That says what it says right there. Draw the constellation diagram. So we've got 4-bit words. With 4 bits, there's 16 possible combinations for the signal. So I'll start with 0, 0, and we will find the quadrature AM signal as a function of time. So the symbol is not 0, 0, but 0, 0, 0, 0. We're using 4 bits. 2 bits for the more significant bits, 2 bits for the least significant bits. Both of these map to -3. So the in-phase signal is -3, and the quadrature signal is -3. So we have, for the in-phase carrier, -3 times cosine. So let me put the minus into a phase shift and call this 3 times cosine 2 pi FCT minus 180 degrees. Okay, so I'm sorry, there we go. This is minus, so the least significant bits, 0, 0, maps to -3. So we have -3 times cosine. So I'll put the minus sign into the phase angle, 3 cosine 2 pi FCT, and we're adding to that the signal through the bottom. That's the more significant bits. Again, 0, 0 maps to -3. So this is -3 times the quadrature carrier, 2 pi FCT. And now let's put the minus sign into the phase angle. So we've got a -180 and a -90. So the total is -270 degrees. Okay, so this is the signal that we are going to draw to map onto the constellation diagram. So let me start with the real axis and the imaginary axis, and let's see if I can keep this. Okay, let's put the real axis here. This is the imaginary axis, and I'm putting in some tick marks. So we want to plot the phasors for these 2 sinusoids. The first has an amplitude of 3 and an angle of -180 degrees. So that's an amplitude of 1, 2, 3. So the arrow points to here, and the angle is -180. That's to this point. The next has an amplitude of 3 and an angle of minus 270 degrees. So minus 270 degrees and a magnitude of 1, 2, 3, and this takes is a vector that points to that point. When we add the two vectors together, we get a point that falls. If I can hit it right there, this is the point in the constellation diagram that corresponds to the symbol 0, 0, 0, 0. So this is for 0, 0, 0, 0. Okay, let's go to the next, which is 0, 0, 0, 1. The quadrature AM signal is now the least significant bits are 0, 1, and 0, 1 maps to minus 1, so that's going to make the value of the in-phase signal minus 1 times this cosine, so that's going to be 1 times the cosine of 2 pi FCT, and I'll put the minus sign into the phase shift. And then 0, 0 maps to exactly this same signal again, plus 3 cosine 2 pi FCT minus 270 degrees. And now we plot the phasors. We have 1 with an angle of minus 180. That points to this line. This is 1 with an angle of minus 180 plus 3 with an angle of minus 270. So plus 3 with an angle of minus 270 gets us to, it looks like this point right there. So this point in the constellation diagram is for 0, 0, 0, 1. And let's do a couple more, see if we can see a pattern developing. The next one would be 0, 0, 1, 0. 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. The QAM signal. Now the least significant bit is 1, 0. That corresponds to plus 1. So that's going to be 1 cosine 2 pi FCT minus 0 degrees, because we're multiplying by plus 1. And then for the more significant bit, 0, 0, we get the same, plus 3 cosine 2 pi FCT minus 270 degrees. And we draw the phasor. We have, oops, that's all right. We have 1 with an angle of 0 plus 3 with an angle of minus 270 right there for 0, 0, 1, 0. And I'm willing to bet 0, 0, 1, 1 falls right here. But let's 0, 0, 1, 1 phi QAM. The two least significant bits map to plus 3, so that's going to be 3 times cosine 2 pi FCT minus 0, because it's got a plus sign. And then for 0, 0, we get the same, 3 times the cosine 2 pi FCT minus 270 degrees. So an angle of magnitude 3 and an angle of 0 points out to this direction, magnitude 3, angle 0, plus 3 at an angle of 270, and right there, this is for 0, 0, 1, 1. So those are the first 4 points in a 16 symbol quadrature AM signal. Let me stop the recording, and I'll think about where the rest of them fall. I've completed the equations for all 16 of the symbols in this 16 symbol quadrature AM system. And there's symbols 0, 1, 2, 3, 4, 5, 6, 7. And here symbols 8, 9, 10, 11, 12, 13, 14, and 15, and you can look through them at your convenience. And this is the 16 symbol constellation diagram with all 16 of the symbols at an individual point in the constellation diagram. This is clearly different amplitudes for different symbols. These 4 symbols in the middle have an amplitude of square root of 2. 1, 2, 3, 4, 5, 6, 7, 8 symbols have an amplitude of square root of 10. And then 1, 2, 3, 4 symbols have an amplitude of the square root of 18. Now, this is just one way of making a 16 symbol quadrature AM system, and the constellation diagram for it. These points can be placed any number of places depending upon the particulars of the system. And who's to say, without more analysis, which constellation diagram is more appropriate? If you Google constellation diagram on your computer, this is the page that will come up, and it shows several examples of how constellation diagrams may be designed. This is a 3-bit constellation diagram with 1, 2, 3, 4, 5, 6, 7, 8 symbols, 0, 0, 0 through 1, 1, 1. That's one way of doing it. Here is a different way of doing a 16 symbol constellation diagram with different locations and amplitudes and phase angles for the symbols. Now, some of these designs may be preferred over other designs depending upon other circumstances in designing the system. So, and that's thankfully beyond the scope of our course. So feel free to look around and see the various possibilities with constellation diagrams. I want to go through demodulation of the 16 symbol QAM, quadrature amplitude modulation digital signal, but I'm certainly not going to do all 16. So I'm going to pick one, maybe representative, and go through that demodulation. And the one I pick is, let's see, which one do I pick? I don't want to tell you. So let's take 3 times cosine 2 pi FCT minus 180 degrees plus 1 times cosine 2 pi FCT minus 270 degrees. Okay, so this is the quadrature AM signal for a particular symbol, and I want to see what symbol that is by the process of this synchronous demodulation. So the signal is applied to a mixer and mixed with this cosine passed through a low-pass filter. Let's call this signal R1 of T. Make R1 of T equal to the low-pass filtered version of this signal. 3 times the cosine 2 pi FCT minus 180 degrees plus 1 times the cosine 2 pi FCT minus 270 degrees. We're going to multiply that by cosine 2 pi FCT. Okay, so this sum of these two cosines multiplies this cosine, then we low pass filter. That makes R1 of t equal to the low pass filtered version of cosine times cosine. Let me apply the trig identity. We have 1/2 times 3 3/2 cosine of the difference of the two angles, 2 pi FCT minus 180 minus 2 pi FCT just leaves minus 180, plus 3/2 cosine of the sum of the two angles, 2 pi times 2 FCT minus 180. And then the other multiplication gives us plus 1/2 cosine the difference of the angles minus 270 degrees plus 1/2 cosine 2 pi times 2 FCT minus 270 degrees. So cosine of minus 180 is minus 1. Cosine of minus 270 is 0. Low pass filter takes out the two high frequency components. Then R1 of t is going to be equal to minus 1 times 3/2 minus 3/2 minus 3/2, which we've got the thing scaled by 1/2 because of the trig identity, but we could easily amplify this by a factor of 2, and this minus 3 on our chart maps to a 0, 0, which is the least significant bits. So this maps to the symbol 0, 0 for the least significant bits. Then if we find R2 of t, that's equal to the low pass filtered version of, again, 3 cosine 2 pi FCT minus 180 degrees plus 1 cosine 2 pi FCT minus 270 degrees, and that all multiplies cosine 2 pi FCT minus 90 degrees. Here we're multiplying by the phase shifted version of the carrier, and that makes the signal the low pass filtered version of, see, we have cosine times a cosine. It gives us 3/2 cosine of the difference of the angles, which is going to be minus 180 minus a negative 90, so that ends up to be minus 90 degrees, plus 3/2 cosine of the sum of the angles, 2 pi times 2 FCT minus 270 degrees, plus for the other cosine times a cosine is 1/2 cosine the difference of the angles, minus 270 plus 90 would give us minus 180 degrees, plus 1/2 cosine of the sum, and that's going to be looks like minus 360 degrees. The cosine of minus 90 is 0. Cosine of minus 180 is minus 1. The low pass filter takes out the high frequency components, and so that makes R2 equal minus 1/2. See if we multiplied that. Don't know how much of that was not on the screen. We have -1/2. Multiply that by 2 and it maps to -1, which is 0, 1 for the symbol. This is 0, 1 for the most significant bits. So the symbol is 0, 1, 0, 0, and sure enough, if you look at the equation for 0, 1, 0, 1, I'm sorry, 0, 1, 0, 0, we have 3 cosine 2 pi FCT minus 180 plus 1 cosine 2 pi FCT minus 270, and that's the one I was working on. Okay, so synchronous demodulation can recover the proper values. These values are then, through the analog to digital converter, are mapped to a 2-bit word, which are then through a shift register formed into the 4-bit symbol. And let's see, I'm just going to do one, because I certainly don't want to do all 16, because they'll all work out exactly the same, similar fashion. Okay.